So because using SRAM4 isn't as fast as using some of these other memory types. So for example, on SPI1, I think it would be faster for us to use SRAM1, which is part of this DMA, right? If you have a look at the bus diagram, you'll see it's more closely coupled, right? Yeah, that's right. But this made it easy because it means we can just have a single DMA memory allocation function, right? And what that does is that gives us a very simple way of allocating DMA memory, right? And usually, because the total bandwidth for DMA in ArduPilot isn't all that high, so usually we are not DMA bandwidth limited. And so that was the excuse I used, but it really isn't as efficient as if we did it properly. And what we need to do is have a separate DMA allocation function for each peripheral type, right, to really do it properly. The other thing that I didn't do, so the H7 in there, so in the primary DMA, there's DMA1 and DMA2, right, in these main DMA, and it has a total of 16 channels available to it. And something like SPI1, both the receive and can transmit, can use any of those 16 channels. But ArduPilot was built around allocating DMA channels at compile time, right? Because I originally designed the DMA system for ArduPilot based on the F4 and the F7, and then later on things like an F3 for AP-perif. And I didn't come across to the H7 till quite a bit later. And so ArduPilot assumes that all of the DMA channels, which DMA channel a peripheral is going to be used, is allocated at compile time. And so when you go and do this build, if I go and have a look at build TDH and the hwdef.h, you'll see this section. This is the DMA mapping for all the peripherals, right? This is all the peripherals that you're using. And we're allocating at compile time the DMA mappings to use. Okay. Now, it would be better if we didn't do that. It would be much better if we made the decision at runtime based on the utilization. So I've got a plan where I'm planning to basically encode these tables, not just for the H7, but also for things like the F7 and others. Encode these tables into Flash and make the decisions at runtime instead of at compile time. And by what we'll be doing is looking at the utilization level of the channel and picking the least utilized channel of the ones that it's able to use. And so what I'm thinking of doing is creating a mask, like a DMA cap mask, right? Which might be something like 003000 for something like F7, meaning it can use these two channels out of 16, right? And then for the H7, it would be 0x like that, right? Because it can use any of them, right? And then what it would do is we would keep counters for the number of microseconds we've used each of the DMA channels. And then when it's going to allocate a DMA channel for a task, it would look for the channel which is least utilized. And so it would naturally align with the available channels on both F4, F7, and H7. And I think that would be a much better design. It would allow for better DMA sharing. So that's what I would like to do long term. But what we did instead, we've got this DMA resolver.py, right, and it's got this little thing here, generate DMA mux map mask, right? And what that does is that creates a fake version of that DMA map for the H7. Okay. So if you turn on debug true in this, like that, and you do WAF configure minus minus board TDH pipe through less, what you'll see is it's actually created a fake mapping here, right? And it's creating that as using these rules, because there are still rules on H7 as to what DMA channels are allowed to use. The main rule is you can't use obviously the same channel for both the transmit and the receive of the same peripheral. So you can't use the same channel for SPI1 transmit and SPI1 receive, right? Because then they'd both be trying to, if you're doing a simultaneous transmit receive on SPI, they'd be overwriting each other. Okay, so that's one of the main constraints. And there are a few other constraints as well. So basically, this DMA map is an attempt to create a fake version of this map for the H7, right? But it's definitely not optimal. And I've noticed that I've actually been working on a patch just in the last week or so to make it a bit more efficient, because sometimes it leaves channels unused. And like on Cube Orange at the moment, if you do a build on Cube Orange, so if I do Cube Orange, and so if I generate the hw.h, so build Cube Orange, def.h, and resolve, and I've got a lot of sharing here going on, right? And you can see that I'm using, okay, so 1.1 is being used here somewhere. There's basically one channel that's not being used. So there's 1.0, 1.1, 1.2, 1, 1, 2, 1.3, 1.4, 1.5. Is 1.5 being used? Yes, 1.5 is being used. There's one, I think it might be 2.5. Yes, 2.5 is not being used, right? 2.5 is not being used at all, which is terrible, because we're sharing this one, with all of these peripherals sharing, and we're wasting a channel. There's a completely unused channel, 2.5, which is it's completely silly, right? And it's just because this code here is just not very efficient. It's got some, bugs in it, basically. And so I'd like to improve that even better if I can make it runtime instead of compile time. But you've also got the BDMA, and then you've got the SDMMC, which is a different DMA. So there's actually an awful lot of DMA channels on H7. And you're only using the first two DMA peripherals, DMA1 and DMA2, which actually means you're wasting a lot of channels as well, because you could be using DMA, the BDMA, right? And BDMA, so BDMA can be used for example, SPI6, and it's also can be used for I2C4, can use BDMA, right? And so if you actually switched one of your I2C channels to I2C4 and one of your SPIs to SPI6, that would allow you to use the 8 BDMA channels, which would free up the channels, 4 channels from your main DMA controllers, which means you could probably get down to no sharing at all. But there's bugs. The H7 is a very new chip, and it has lots of bugs. So I discovered, for example, when you're using I2C4 and SPI6, that you can't use neighboring channels for the receive and the transmit on the same peripheral, right? So you should be able to use, for example, channel 2 for transmit on SPI6 and channel 3 for receive, because they're independent channels, no problem. But that's right, but there is a problem. It turns out there's a bug, and hardware bug. And if you do that, it'll work most of the time, but just occasionally you'll get failed DMA transfers. But if you move it so that the two channels aren't adjacent, so that they're like channels 1 and 4, you don't get the bug. You get reliable DMA transfers. So you get all these little odd things happening with H7. It was a real challenge. I spent about 3 months doing the initial port of the 8 to the H7, and it was quite exciting because there was all these little, odd things to discover, little things to discover about, what was wrong, what wasn't working. Um, but anyway, back to the original thing. So, you being puzzled about H7 DMA is not surprising because we use it in a fairly odd fashion. And I'm hoping in the future we'll use it more efficiently. Um, so back to your watchdog. Have you have you had the watchdog on any build that does include that fix that I pointed you at this evening? So it won't be a DMA sharing problem because the SDMMC actually uses its own DMA peripheral, completely separate from all the others. It's a weird one, and so so I don't think it could be a DMA problem, right? But it won't be. It won't be a DMA sharing problem. And what it'll be is, so in this SDMMC V2, you'll notice that this is the DMA controller. It's got this thing called iDMA, right? This iDMA transfer, which is internal DMA. That DMA controller is dedicated to the SDMMC, and it's not used by anything else, or at least in RGPilot. I don't know whether it can be used by anything else. Now, it could be that I've got bugs in that because I wrote that driver. It took me quite a long time to get SDMMC to work. I did have a lot of issues with it, and it could be that I've got some bugs in that. Do you have all of the pins plumbed through for SDMMC, or are you using a subset? Mm. Okay. Have you checked whether you're using the same SDMMC pinout as is being used by the other H7 boards that RGPilot supports? So you can see the schematics here. So if you have a look at something like this, RGPilot schematics, right, you'll find some schematics for various boards that RGPilot supports. Not all of the boards are here, but for example, you could look at the Durandal, which is an H7. It's got the full schematics for the Durandal. You could compare there. You can also look at the CUAV, the X7, and the Nora. They are both H7 boards. And I don't think the Cube Orange has got the schematics. It's no, it's only got the Cube Black schematics. But there, you do have the other ones. The CUAV and the Holybro ones are available. And you could compare whether you've got anything different for the SDMMC. Um, see if there's any pull up, pull down differences that might explain the issue. But it would be nice to track down the problem. I'd very much like you to capture as many of the watchdogs as you can, because the watchdog doesn't always produce a useful address. I'm still a bit puzzled as to why I don't get the same address you get. So if I run GDB, this is the RGplane binary here that you gave to me, right? And if I disassemble, so let's see, mav log dump minus type wdog 20 tail -2. Right. So this is the critical address, the LR, right? And if I disass that, then you can see that this function is inside chvt do reset I. Okay. Now, that I was actually quite pleased to see that, because that function is related to this fix that I did last week for this existing watchdog, right? Because there's a virtual timer we're using, and there was a race condition with this virtual timer. So I thought, great, maybe it's the same bug. But what puzzles me is this: if I build it, so I've got, let's see, if I do type message 20, and you can see that the build you had, this was the build, right? The git hash that you had. And that's exactly the git hash I've got here, apart from where I did that true false, right? And I've got exactly the same tools bootloader, the TDH that you gave me. Okay. So if I do build yours and I build that like that, then I don't end up with the same binary that you did. So, right, so wait for that to build. And then I run against that, and ups, I've got the wrong paste. So grab that and paste that in, and I get this function, ch scheduler ready. Now that's the base task switcher, right? The scheduler ready is to do with the core RTOS task switching, and it's a totally different function. So there's a couple of things that puzzle me. One is, why can't I build the same binary as you? And there must be something different about our build environments. It should. I spent some time last year trying. We always ended up at the same binary, and I did make sure that the hwdef.h is the same, right? Because, right, there's the hwdef.h that you sent me, and there's the one. That means the configure came out the same, because the hwdef.h is identical, right? So if the configure's the same, and I'm running exactly the same compiler as you, then I don't understand why, if I, same compiler, same configure, why is it different? And I don't know whether, did you give me exactly the bootloader? This bootloader is embedded in ROMFS, so that file has to be the same, because it gets compressed and embedded in ROMFS. And I don't know if that's the same. And let's see if the size is the same. None EABI size build TDH bin RGplane. All right, and that's let's shove that into my Scratch, and then your one. Non-EABI size RGplane, that one. I'm really sleepy. All right. So, yeah, so you've got, your binary is 2 kilobytes smaller. Ah, right. Okay. Yes. Now, do you use, I assume you use two flash pages, not one. Right. Okay. Let's just have a look at the flash layout. HWDEF common flash dot C H7. So it's got and it's 2048 on 120 fixed flash size, so 16. So you should be using 14 and 15 last two pages. That should have been okay. That should work. The flash is very strange on H7, but there is one board that is using the Matec H743 is the yeah, that's the only one other one that's using flash for storage, and it's not great using flash for storage because if it has to recycle the page, if you fill the page and it has to erase it, when you erase the page, the microcontroller stops completely. Yeah, we actually do try to prevent it. It depends whether it lasts long enough, how long it takes to erase the page. Doesn't always cause a watchdog, but it can. And it's a bit unfortunate because there's not really anything we can do about it. The only way we could prevent it is if we put the flash erase code, we actually moved it into RAM. So we'd have to use linker tricks to shift that into RAM. And that's something that I'd quite like to do because that would make it safer to do this. But what we do is we make sure we never erase a page when we're armed. And so we don't do that erase when we're armed, which means we're not going to actually crash a vehicle. But we should really be copying the critical code into RAM and then execute it from RAM instead of from flash, because the CPU only stops if the CPU tries to access a flash page in the same bank as the one that's being erased, as the page as the bank of the page that's being erased. So yeah, anyway, it'd be quite nice to do, copy it to RAM and things, but I don't think that could have caused that problem in flight for you. Yeah. So um, yeah, okay. So if you can possibly run with the enabler certs for a while, and you may find that with enabler certs it doesn't boot at all, right? Because there might be an assert that comes up immediately. And if there is, then we need to get the debugger on it and try to find the cause. Do you have a debugger available? Oh, great. Okay. You can use ST-Link. That's great. So if you do find that it doesn't boot with the enable asserts, or if you find that it regularly faults, then what we can do is we can get a debugger on it and find the fault. But I think it would be very interesting to test. Don't try and fly with enable asserts, but just test it on the ground with the asserts and see how it goes. And yeah, so all right, so try that for a while and see if you can find a way to reproduce the problem. If you can, so is the pinout of your board roughly the same as like the H7, the Matec one, or is it very similar to one of the existing boards? Well, I'm wondering if I can try and reproduce the problem as well. So if any of I'd have to go and have a look. So did you base your pinout on one of the existing boards? Right, I see. So yeah, I was just thinking I could try to reproduce the problem, because I'd love to be. I really want to get to the bottom of this. It might be that the problem disappears now that with that bug fix that I put in a couple of weeks ago. If it does keep happening, then I'd like to keep investigating with you and find the real cause. And part of that would be, if I can try to reproduce the problem myself, or if I can help you with, get set up with the debugger or using the debugger, and or to add more debug code in. But I think the first step is just to run it with the asserts enabled and see if we can reproduce. Yeah. Okay, that's great. And so if you record, when you get a watchdog, record all the data from the watchdog, like the wdog file, sorry, the log file, and it should also be coming across Mavlink as well in your T-log. And then also keep a copy of the exact arduplane binary, um, and the hwdef.dat and the bootloader file. Yeah, just keep a copy of that so that we can try to confirm that get disassembly and the backtrace and the address that it happens on. Um, and that would be really useful. There are a few things we can see from this, right? So the FP, that's the fault priority. That's the priority um, of the thread that was running at the time that the fault happened. Okay. And so that is the main priority. Okay. Which means it was running the main thread at the time. We can also see the thread name. The thread name started with ardu. So that's going to be arduplane, right? Or ardupilot, which is the main thread. Okay. We can also see that it doesn't hold any semaphores. There were no semaphores being held. We can see that it was a hard fault. In this particular case, this one was task 19. Now, we should look up, I haven't actually done this yet, to find out what task 19 is. So this is, let me just go and look up task 19. So now this is I got the right, yeah, I've got the right one there. And so what it will be, if we go arduplane, plane.cp. Oh, sorry. Yes. Sorry, I turned off my screen share. I was thinking we were done with the screen share, but I'll turn it back on again. All right. Okay, no worries. So these are the scheduler tasks. All right. And so it'll be task number 19 here. And so what we've got to do, it's a little bit tricky. And so let me go and have a look. So persistent data task equals I. All right. So what it does is it puts a task number in here when it's about to run the task. All right. And let's see what the task number was for the other one, and whether it was the same task. And task was 0, so different task. All right. So it might mean that it's not relevant at all. We might as well look up what it was anyway. So now, this is task 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19. Update send. So it was in the update send, which is the ground station send. So that was basically trying to talk to your ground station at the time the fault happened. And that isn't necessarily, the fact that it was different for the two different times it crashed might mean that this is completely irrelevant. And that it was in fact just an interrupt completion. And that's where I suspect it's a timer, completion of a timer that has been reset. And we've got a sort of a timer completion happening as a race condition. But yeah, so that's my sort of guess on it. But I really don't know. Yeah, I really don't know. And that's where, if we can try to reproduce it, that would be really, really handy. Um, yeah. Yep. Okay, fantastic. Yep. I hope your plane wasn't destroyed too badly. Is it going to fly again? Okay, great. Right. Okay. Yeah. Oh well, I hope you're able to fly it again. But let's try to get to the bottom of this. And I'm around most evenings, and hopefully we'll be able to catch up and get to the bottom of the what's going on. Yeah. Yeah. Well, it's hard to say. We're just sort of guessing at this stage. Yeah. All good. Okay. Well, good night. Well, thank you. Thank you for helping us chase it down. Oh well, I'm delighted to talk to you as well. Always want to help out, users of Archipilot. Okay, right? Okay. Good luck. Right. Good night.